Alright, so what we're going to demonstrate here is an application of Lenz's law, and we're talking about electromagnetic induction. And so the important thing to note with the electromagnetic induction is that there's no power source of any kind. And so essentially what we're doing is we're just using just a magnet, and just using the magnet we're actually going to cause current to flow through, in this case, the solenoid. And we've actually connected a galvanometer into the circuit, and a galvanometer is basically just a giant ammeter, and you can see that it actually measures in microamps. That's what it measures in. So what we're going to actually notice is that when I actually take this magnet, and as soon as I move the magnet in towards the solenoid, so remember what a solenoid is it's just going to be, it's just a lot of coils of wire just wrapped around a core, and let's move that wire out of the way there, and we can see it's just basically hollow inside. Okay, so it's just basically a coil of wire just wrapped around a cylinder, ultimately is what that is. So we've got a lot of wire there. I'm going to take this magnet, so you see the North Pole is marked off there, and we're going to see that as I move it in towards the solenoid, that we're actually going to see some current that's going to flow through, and that's going to be actually displayed on the galvanometer. Now it's not going to be very much. That's important to note, that we're just going to get a very, very small current. Remember, that's measuring it in microamps, so that's a millionth of an amp. So we're going to get a very, very small amount of current flowing through. Nothing significant, but it still shows a relationship between electricity and magnetism. Okay, so I'm going to take this North Pole, and I'm going to move it in towards the solenoid, and we're going to see what the effect is. Okay, so I'm doing this. Let's see what the effect is. And I can see it's very small, but there's definitely a noticeable current that is flowing through. So this is when obviously I'm doing nothing. So obviously what I'm doing is having an impact. And let's just see, because I was moving it back and forth, so let's just see when I move the North Pole, so I'm moving the North Pole in, let's see what direction that actually causes the needle to go. So I move the North Pole in, and so we actually see what happens. So and see when I moved the North Pole out, it actually went the other way. So moving North Pole in, I saw a deflection to the left, a very small one, and then went to zero very quickly. So notice that when I'm not moving the magnet, because the magnet is still halfway in there, nothing's happening. Okay, but then as soon as I then pull it out, the needle then deflects in the opposite direction. So that's going to be important, and we're going to explain this using Lenz's law. Now, I'm not going to continue to use the galvanometer. It looks nice, you know, it's very big, it's a very large display, but obviously the deflections are extremely small. Okay, so what I'm going to use instead is I'm going to actually use this here, which is also a microammeter, but it is going to deflect a lot. Okay, so we're going to see a much more noticeable deflection of the needle on either side, and that way it's just going to be, I guess, a bit nicer of a visual. So I'll go ahead and set that up. Okay, so I've actually grabbed just another microammeter. Now actually I think I'm going to switch this out for a milliammeter, and the reason is showing you that the deflection, you remember how small the deflection was on the galvanometer, but now looking at the deflection we're seeing it's off the charts. Okay, so I'm moving the North Pole in to the right, and I move it out to the left, and it's getting maxed out on either side quite easily, which, I mean, it's great in one sense because it's much more noticeable. But I also want to then demonstrate how increasing or decreasing the speed is going to actually increase or decrease the deflection. And if I'm just going in slow and it's already going off the charts, we're really not going to be able to actually see that. So what I'm going to do is actually replace it with this microamp or this milliammeter. Okay, so remember that milli, that's a thousandth, and so we're talking about bigger units here. So a big deflection on here in terms of microamps is going to be a smaller deflection on here in terms of milliamps, right? Remember that a milliamp is a thousandth, a microamp is a millionth. That means that this unit here of milliamp is 1,000 times bigger than this unit here. So a deflection here, theoretically, what should happen is that a deflection here should be about 1,000 times smaller a deflection on this one. Okay. Now in actuality, it's not going to be 1,000 times smaller necessarily. In practice, it's still going to be quite noticeable, but it's not going to go off the charts. So I'm going to go ahead and actually put this milliammeter in. Okay, so now I've got the milliammeter in there. Okay, and so again, North Pole in. I can get it in there. A bit hard to do it looking through the camera. And so now, again, I can see a deflection, and it's more noticeable than it was with the galvanometer, much more noticeable. And so all I'm doing is I'm just oscillating the North Pole in and out, and I can see how that's causing the needle to deflect. Okay, so as it comes out, it's going to the left. As soon as it stops, back to 0. And then when it goes in, it deflects to the right, quickly back to 0. As soon as the magnet stops, the current stops flowing. And that's an important key there. Okay, so and I can also then see, because it's not getting maxed off, the charts, like it was with the micro ammeter, I can see also how the speed affects it. So let's just look at that really quickly. Okay, so this is sort of just going in slow, in fast, out fast. And we can see that there definitely is I'm going faster and faster and faster, and I'm seeing that there definitely is, so they slow, yeah, smaller deflection, and then now I'm just going to start going faster and faster and faster, and definitely seeing there's quite a change in the deflection that we're getting. Okay, so then the question, of course, is how do we explain what we're actually seeing here? And this is explained using Lenz's law. All right, so the idea is that as this North Pole goes into the solenoid, what's going to actually happen is that we're going to get, we're going to get what we call a change in flux. Okay, so we can think of flux as being all of these sort of invisible magnetic field lines that come out of this magnet. Of course, we can't see them, so we're going to have to visualize what they look like. So they're all coming out of this magnet, and of course they're going to go out in sort of all different directions, and as it goes away from the magnet, of course, they're going to get further and further apart. Right? They're going to decrease. Right? So obviously the magnetic field strength decreases quite rapidly as we move away from the magnet. Okay? But we've got all these different magnetic field lines. Now some of those field lines are going to actually pass through right here. Sorry, that's just the power cord for the camera. It's out of battery. But some of those field lines are going to actually pass through the solenoid. Okay, and that's what we call the flux. Okay, now what's going to happen, because the magnetic field lines are very sort of densely packed at the North Pole and very densely packed also at the South Pole, is that as this North Pole moves closer to the solenoid, we're actually going to end up getting more magnetic field lines that actually pass through the solenoid. In other words, the flux increases. Okay, so again, just the definition of flux. We're talking about the number of magnetic field lines, but not just the ones that are coming out of the magnet. That's not really what we care about. We care about the number of field lines that actually are passing through this cross section of the solenoid, which of course is a circle. Okay, so that's what we're calling the flux. And so it should be very clear that because I'm getting a lot of field lines coming out of the North Pole, that the closer that I put the North Pole to the solenoid, the more magnetic field lines are passing through. And of course then as I pull it away, obviously the flux is again now going to be decreasing. Okay, so flux increasing, flux increasing, flux decreasing, and obviously that as the flux increases or decreases, that we're getting a current that flows. Now of course when the flux just stays constant, the flux is not changing, so I can see here the magnet's just sitting there, the number of field lines that are passing through the solenoid is not changing at all, then we're getting a whole lot of nothing. We're getting no current flowing through. So it would appear that the flux is really the key, and more so than that is the change in flux that is going to actually produce a current. Okay? And so what Lenz's law states is it doesn't really talk necessarily about why this happens. It's not really an explanation for it. This is why we actually get a current that flows through. That is more so to do with Faraday's law, which will be what we'll talk about in a different video. Lenz's law is more so just describing what actually happens in terms of, well, it's going to allow us to predict the direction of the current flow. Okay, so I can actually see, looking at the terminals of the battery, so that this is the plus, This is the positive terminal. This is the negative terminal. Okay? So if current flows through this way, so if it's going around sort of anti-clockwise in this case, well, that's going to indicate a positive current. It's going to go to the right. Okay? Now, if current is flowing the opposite direction, so it's flowing around, now it's going around clockwise, so it's going from negative to positive, so it's going around this way, well, that's going to be a negative current, and we'd expect that the needle would go to the left in that situation. Okay? So let's just remind ourselves which way is which. So when the North Pole goes in, we're getting a positive current. Right? We saw that. And as the North Pole comes out, we're getting a negative. Positive in, negative out. Okay? Now what Lenz's law says is that he said, well, let's think about how the flux is changing. Okay? So we have to think about the field lines. And we know that the field lines go from the north and they're going around to the south. So from north around to the south. Okay? So we would say that obviously the flux in this case, which is going to be the direction of the field lines, is going to be to the right because the North Pole is on the right. And I can see that it's going to be increasing. It's going to be increasing in this case. So what he said is that that is then going to induce a flux in this coil. And that induced flux has to oppose the change in flux. And it's a bit confusing thinking of the language, so maybe we just sort of unpack that and see what that means. As the flux, so remember the flux is to the right and increasing, what's going to happen is that we're going to get in the coil, in the solenoid, we're going to get a flux that's going to then oppose that change. So we have to think about what the opposite is. Okay? So the opposite of to the right and increasing, and some people might think, well, that's going to be to the left and decreasing, but that's actually not the case. Okay, what is actually the opposite of to the right and increasing is to the left and increasing. Okay, so let's just keep that in mind as we think about Lenz's law. So we've got this magnet is coming in and the flux is increasing to the right. Okay, so the magnet is coming in. We're getting an increasing flux to the right. Lenz's law tells us that we're going to get an induced flux in the solenoid that will oppose that. Oppose, so it's going to be the opposite of increasing to the right. It's going to be increasing to the left. So inside the solenoid, and so this wire, this black one here is just a power cable, so don't necessarily pay attention to that. It's not involved in this demonstration, is that we're going to actually get in the solenoid a flux that's going to be to the left and increasing when that magnet comes in. Okay? Now what we can do then is, I know that if I've got a magnetic flux to the left, what that's going to do, and because we've actually learned before that in a wire, that when I have current that flows through the wire, I can point my thumb in the direction that the current flows, and my fingers indicate the field lines around the wire. But there's also a second way that we can use what we call the right-hand grip rule. So this is the right-hand grip rule. It actually has two uses. So one is that, the wire, this is my current direction. My fingers then trace the magnetic field lines. But we can also go the other way as well. And my thumb, and we're talking about induction, my thumb is going to point towards the magnetic, in this case, north. Okay? So my thumb points towards the magnetic north, and then my fingers are going to indicate the direction that current then flows through the coil. Okay? So let's just sort of put it all together now and see if we can actually predict that what the direction is going to be of the current that flows through the solenoid. Okay, so remember, flux is to the right, increasing. Okay, so flux is to the right and increasing. And what that means is that inside the coil, inside the solenoid, we're going to get a flux towards the left and increasing. My fingers then indicate the direction that the current flows through the solenoid, which is going to be around this way. And now I just need to sort of deduce, and this is always a bit tricky to see, well, what does that actually mean in terms of, is it flowing from this side to this side or this side to this side? So let's just do a little investigation. So again, it's going to be flowing around this way. Now what I can see, if we look closely here, I can see that the coil is actually wrapped around this way. If we look at that very, very closely, I can see the coil is wrapped around this way. Okay? So if it was, let's say that my fingers coiled around if my finger's coiled around this way, then that means it would be following this from the green and then following it around, and it's going to be wrapped around like so and eventually come out through the yellow. But that's not what we have in this case. We have actually the opposite, which is that it's going this way, which means it's actually going from the yellow around towards the green. So it's going from the yellow to the green, then it's going to go through the positive terminal, through the negative, and then back to complete the circuit. Okay, so what we would expect in that case is that I'd expect in that situation that we should actually have a current that's flowing from yellow to green, through the positive to the negative, and I would expect to see a deflection in the positive direction. Now I've already forgotten which way it went, but let's just check and see if we're actually right. So as the flux increases to the right, that means that we're going to get the induced flux is going to be to the left. It's going to go around this way, which means it's going to go from the yellow around to the green and around the circuit like so. It's going into the positive, so I expect it's going to actually deflect in the positive direction. Let's just see if that actually does happen. So here we go. And I see that I'm actually correct. As the North Pole goes in, it does deflect in the positive direction. Now as the North Pole comes out, it deflects in the opposite direction. We can explain that the same way. So what's happening when it's actually coming out? So it's coming out, well, the flux direction is still the same. It's still coming out of the north, so it's still directed towards the right, but obviously it's going to be decreasing. So the change in flux is to the right and decreasing. Okay, well, what's the opposite of to the right and decreasing? Well, it's going to be to the right and increasing. So again, I take my right hand grip to the right and increasing. So it's going to be going around this way, like so. And just based on, so again, it's going around this way. Sorry, it's a bit difficult to sort of show this. Now, if you remember, we've actually got this wire that comes out of the green, and that's actually the way that it's actually wound around. So it's going to be from the green wire around, wrapped around to the yellow, and the current's going to then enter through the negative terminal of the ammeter and go towards the positive terminal. And so I'd expect, well, that means we're going to have a negative current. And so when I'm moving the North Pole out, I expect to see that the needle will deflect in the negative direction. And we can see it does. So when it goes in, positive, it comes out negative. Now we can apply a similar argument with the South Pole, and the South Pole going in or out. So when the South Pole is going in, well, we can think of this as, well, again, we still have, now in this case, we've got the flux is to the left, okay? And so the flux is to the left, and it's going to be increasing. So the flux is to the left and increasing. And you might say, okay, so I accept the fact that the flux is to the left, because obviously that's the North Pole, and it's always going to be directed away from the North Pole. But why is it increasing? Well, the North Pole is still moving closer to the solenoid. So we're still going to have more field lines that are going to go through the solenoid. Okay, so the only real difference here is just the direction of the flux. Instead of it being directed to the right like before and increasing, now it's directed to the left, but it's still going to be increasing. Okay, so let's again use our Lenz's law to figure out what's going on. So the induced flux is going to be, well, to the right and increasing. Okay, so it's going to be to the right and increasing. Okay, so my fingers are going to then indicate the direction of the current flow, and again I can see that it's going to be going around from, sorry, I'll just bring the camera down here. It's going to be going around this way, so again to the right and increasing, so my finger is going to go around that way, and I can see that it's going to be going from the green, and it's going to be going around to the yellow, and it's going to be actually going through the negative terminal in the ammeter. So what we're interested in here is the direction that the current is flowing through the ammeter. That's really the key. And where is it entering the ammeter? And if it's entering the ammeter through the negative, that means that we actually have a negative current flow. Okay, so I'd expect to see in this case, as I put the South Pole into the solenoid, I'd expect to see a deflection towards the negative. Let's just see if we do see that, and I do. So maybe go a bit more, see a bit more of a deflection. The faster I move it, the more the deflection is. But I can see very clearly that as the South Pole goes in, it deflects towards the negative. Now I can make, just for the last case here, where the South Pole is coming out, it's the same idea. We've got a north pole here towards the left, but now because the magnet is actually moving away from the solenoid, we're actually getting less field lines that are cutting through the solenoid, so the flux is actually decreasing. So the way we would describe this when it's coming out is that the flux is to the left, right? The lines always come out of the north pole, and it's to the left and decreasing. Okay? So what's the opposite of to the left and decreasing? Well, of course, that's going to be to the left and increasing. Okay? So my thumb then goes, using my right hand grip rule, my thumb is to the left and increasing. My fingers are then going to indicate the current direction, and it's actually going to go around from the yellow, and it's going to be going around to the green, and it's going to be going through the ammeter in the positive direction, and I'd expect then to see it deflect in the positive direction on the ammeter. So let's just see. So negative when it goes in, as we already talked about, and as it comes out, it's going to go towards the positive. So this is Lenz's law. Now you notice when I talk about Lenz's law, the way I structure the explanation is very important about talking about how the flux is actually changing. So you have to talk about what is the flux, how is it changing? Well, it's to the left and increasing, for example. And so that's the first thing to mention. The second thing to mention is what is going to be the induced flux in the solenoid. Now you notice that when I talk about the induced flux, there's different ways you can frame it. I always frame it in the sense of it's towards the either right or left and increasing. So I always want that second bit to be increasing, okay? Because if I say it's to the right and increasing, that means that I point my thumb to the right. Now if I were to say it's towards the right and decreasing, then it's a bit confusing, okay? Or if I were to say that the flux was to the right and decreasing, then it's a bit confusing. Well, where do I point my thumb? I don't point it to the right because it's not actually increasing in that direction. I have to point it to the left, so it's just a bit confusing. So I always like to frame the induced flux in the form of it's in this direction and it's increasing. So I always want that second bit to be increasing, and that way I know whatever direction that came before it, that's the direction I point my thumb, and then my fingers tell me the current direction, and everything is really quite easy. Okay, so this is Lenz's law. Again, this is not an explanation for why this happens. Lenz's law does not explain that. It does not explain why this happens at all. Okay? It simply allows us to predict what does happen. So it tells us what does happen, but it does not explain why it happens. To get an explanation for why it happens, then we have to actually talk about Faraday's law, and that's going to be in a different video.